Hello and welcome back to another video. In this problem, we're told that the table shows the number n of species of reptiles and amphibians inhabiting Caribbean islands and the area A of the island in square miles. So we have our islands, we have the area of each island, and the number of reptile and amphibian species on that island. So in part A, we are asked to use a power function to model n as a function of A. So the power function for this data is going to look something like this. N is equal to some constant k times a to some constant b, right? This is a power function of a that models n. And the way you use this is you have to take the natural log of both sides. That's our first step. So we have the natural log of n is equal to the natural log of k times a to the b. And if it doesn't seem clear while we're doing this, we are trying to turn this into a linear regression, which we can then find and use to model part B. So we have ln n is equal to the ln of one thing times the other is equal to the sum of their natural logs. So ln of k times ab is equal to ln of k plus ln of a to the b. So the natural log of n is equal to the natural log of k plus, if you have an exponent inside your log, you can bring it out as a coefficient, so b times ln of a. And here we have a linear function. Might not look like that, but if we say let y equal ln of n and z equal ln of a, and we can do one last thing, let c equal ln of k. When we plug these in, we have y is equal to c plus b times z, right? And we have a linear function right here. So now we can use this to get the least squares regression line, the linear regression of the data using y and z. And what we do, or what we get out is, and you can do this on your calculator, you can do this online, right? Just plugging in the values and you'll get an output. You get y is equal to 1.132 plus 0.308 z, right? This is the function that best fits the data, right? Where y is equal to ln of n and z is equal to ln of a, right? For all these data points. So how do we turn this back into something in terms of n and a? Well, let's first plug back in our what we had for our variables. So the ln of n is equal to 1.132 plus 0.308 times the ln of a. How do we get rid of these natural logs? Well, we can raise both sides to, we can raise e to the power of both sides. E to something is equal to e to something only if the actual exponents are equal. So e to the natural log of n, right? This is e log base e of n is just n, is equal to e to the, when you have things being added in the exponents, you can separate them. So this is e to the 1.132 times e to the 0.308 ln of a. So n is equal to, this is roughly 3.105. This term is e to the ln of a, right? And when you have two things being multiplied in your exponent, it's one thing to the other. So e of ln to the a to the power of 0.308. This is n is equal to 3.105. E to the ln of a, e to the log base e of a is just a to the 0.308. And this is the power function that models this data the best, based off of the linear regression that we do in this intermediate step. So now we can actually do part B. I'll do it over here. We have the island of Dominica has an area of 291 square miles. So if we plug in n is equal to 3.105 times 291 to the 0.308, what we get is roughly 17.8. We can round this to 18 and say we would expect to find 18 species of reptiles and amphibians on the island of Dominica based off of this area, based off of this function that we got from this data.